Is the universe infinite, stretching on forever? Or does it have an edge, a point beyond which nothing exists? This question, fundamental to our understanding of the cosmos, has puzzled humankind for millennia. Even with all our technological advancements, we still haven't definitively answered it. What we do know, however, is that the universe is vast, far grander than our ancestors could have ever imagined. Our journey to unraveling this cosmic enigma begins with what we can observe. Imagine standing on the seashore, gazing out at the seemingly endless ocean. You can only see so far, to the horizon where the sky meets the water. Similarly, we have a cosmic horizon, set by the nature of light and the universe's expansion. This boundary defines the observable universe. The observable universe is a sphere, with us at its center. Its radius is 46.5 billion light-years. But the edge of the observable universe isn't the edge of everything. The universe likely extends far beyond this cosmic horizon, perhaps infinitely. To comprehend the universe's true scale and nature, we need to understand how astronomers study distant objects. One crucial tool in their arsenal is the Doppler effect. Named after Austrian physicist Christian Doppler, this phenomenon describes the change in wave frequency as a source moves relative to an observer. Imagine an ambulance siren wailing as it rushes past you. As the ambulance approaches, the sound waves compress, making the pitch higher. As it speeds away, the waves stretch, causing the pitch to drop. This change in pitch is the Doppler effect in action. Light waves, like sound waves, also experience the Doppler effect. When an object emitting light moves towards us, the light waves compress, shifting towards the blue end of the spectrum. This phenomenon is called blue shift. Conversely, when an object moves away, the light waves stretch, shifting towards the red end of the spectrum, known as redshift. In the early 20th century, astronomers made a groundbreaking discovery. Most galaxies in the universe exhibit redshift. This observation implied that these galaxies are moving away from us. Even more astonishing, the farther a galaxy is, the faster it seems to be receding. This discovery revolutionized our understanding of the universe. The redshift of distant galaxies isn't due to their individual movements through space. Instead, it's a consequence of the expansion of space itself. Imagine dots on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they're moving across the surface, but because the surface itself is expanding. Similarly, galaxies are carried along by the expansion of space. The redshift of galaxies, therefore, isn't just a measure of their speed. It's a measure of how much the universe has expanded since the light we observe left those galaxies. This realization laid the foundation for our current understanding of a dynamic, ever-expanding universe. Section 5. Hubble's revelation. In 1929, American astronomer Edwin Hubble made a landmark discovery. By meticulously measuring the distances and redshifts of galaxies, Hubble found a direct correlation. The farther a galaxy, the faster it recedes. This relationship, now known as Hubble's law, provided the first observational evidence for the expansion of the universe. Hubble's discovery wasn't just a confirmation of theoretical predictions. It was a paradigm shift in our cosmic perspective. The universe was no longer a static, unchanging stage. It was a dynamic entity, constantly evolving, driven by forces we were only beginning to comprehend. Hubble's law became a cornerstone of modern cosmology, enabling us to trace the universe's expansion back to its fiery origin in the Big Bang. Hubble's law also gave us a way to estimate the age of the universe. By measuring the rate of expansion, known as the Hubble constant, we can calculate how long ago all matter was concentrated at a single point, the moment of the Big Bang. Current estimates place the universe's age at around 13.8 billion years. Section 6. Dark Mysteries, Expanding Horizons. Hubble's discovery of the expanding universe opened up new mysteries. Astronomers found the expansion rate wasn't slowing down due to gravity. Instead, it seemed to be accelerating. This hinted at an unknown force counteracting gravity. Dubbed dark energy, it makes up 68% of the universe. Its nature remains one of the biggest puzzles in modern physics. Dark matter, making up 27%, adds to the cosmic puzzle. Section 7. Echoes of the Big Bang. As we peer deeper into the cosmos, we're essentially looking back in time. The light from distant galaxies has traveled billions of years to reach us. offering a glimpse of the universe in its youth. Astronomers have discovered a faint afterglow from the Big Bang itself, a relic of the universe's earliest moments. This afterglow, known as the cosmic microwave background radiation, or CMBR, permeates all of space. It's a faint but detectable signal, first discovered in 1964, that provides strong evidence for the Big Bang theory. The CMBR isn't uniform. It contains tiny temperature fluctuations, representing minute density variations in the early universe. These fluctuations, amplified by gravity over billions of years, led to the formation of galaxies and the large-scale structure we observe today. Studying the CMBR allows us to probe the conditions of the early universe, providing invaluable insights into its evolution. Section 8. Beyond the cosmic curtain. The observable universe, vast as it is, might be just a tiny fraction of the entire universe. The true extent of the cosmos remains a mystery, but theoretical models and observations provide tantalizing clues. Some models suggest that the universe is finite but unbounded, like the surface of a sphere. Just like you could travel forever on the surface of a sphere without reaching an edge, the universe might be finite in size, but without boundaries. Other models propose an infinite universe, stretching on forever in all directions. These models are supported by the concept of inflation, a period of exponential expansion in the universe's earliest moments. Inflation theory suggests that the universe expanded far faster than the speed of light for a brief period, potentially smoothing out its curvature and making it appear flat and potentially infinite on large scales. However, these are just theoretical possibilities. We lack definitive evidence to confirm or refute them. The true nature and size of the universe beyond our cosmic horizon remain open questions, driving ongoing research and exploration. Section 9. Faster than light. The idea of the universe expanding faster than the speed of light might seem paradoxical. After all, Einstein's theory of relativity posits that nothing can travel faster than light. However, this cosmic speed limit applies to objects moving through space, not to the expansion of space itself. The expansion of the universe is governed by the laws of general relativity, which allow for space to expand at arbitrary rates. Imagine drawing two dots on a balloon and then inflating it. The distance between the dots increases, and the farther apart the dots, the faster they seem to move away from each other. Similarly, galaxies embedded in the fabric of space-time are carried along by the expansion, even if that expansion exceeds the speed of light over vast distances. This doesn't violate relativity, because the galaxies themselves aren't moving through space faster than light. They're simply being carried along by the expansion of the space they exist within. Section 10. The infinity equation. The concept of an infinite universe is incredibly mind-boggling. If the universe is truly infinite, it implies an infinite amount of matter, stars, galaxies, and even possibilities. It suggests that somewhere out there, every conceivable outcome of every event might be playing out. This notion leads to the fascinating, albeit speculative, idea of parallel universes. If the universe is infinite, there's a chance, however infinitesimal, that there exist regions of space that are identical to our observable universe, or perhaps just slightly different. These regions could contain exact replicas of ourselves, living out lives that are identical or diverge in subtle or dramatic ways. While the idea of parallel universes remains firmly in the realm of science fiction, it highlights the profound implications of an infinite universe. It challenges our understanding of reality and forces us to confront the vastness of what might exist beyond our comprehension. Section 11. The true reward. The question of whether the universe is infinite is ultimately a question about the nature of reality itself. It's a question that has captivated philosophers and scientists for centuries, and it's one that we may never definitively answer. However, the pursuit of this answer, the journey of discovery and exploration, is just as important as the destination. By pushing the boundaries of our knowledge, by peering deeper into the cosmos and refining our understanding of the laws of physics, we gain a deeper appreciation for the universe's grandeur and our place within it. The true reward isn't necessarily finding all the answers, it's the journey of asking the right questions, challenging our assumptions, and expanding our horizons. The universe, in its vastness and mystery, invites us to keep exploring, to keep wondering, and to keep pushing the limits of human understanding. The journey itself is the true reward.